Welcome to the deep dive. Today we are jumping straight into a really high-stakes technical debate, one that really underpins the future of efficient AI.
We're dissecting the battle between integer, or INT, and floating point FP quantization.
And specifically how they handle the massive demands of large language models.
This whole deep dive is built on sources that are tackling a prevailing industry assumption head-on. If you look at the major new AI architectures, they are leaning so heavily into low-precision FP formats.
Like the ones in Nvidia's recent designs, for example.
Right. The conventional wisdom has been that FP is just better at managing the kind of chaotic data distributions you find in LLMs.
So our mission today is to really systematically investigate that assumption. We're looking for the absolute optimal format, the best balance between model accuracy and, the final hardware cost.
And we're looking at it across different levels of data granularity. The question is, can these low-bit integers truly compete with, or maybe even surpass, the flexibility of floating point?
Well, the core of the problem, as you said, is that data distribution, especially in the activation layers, they have these significant outliers.
These are values that are huge in magnitude, but they don't appear very often. And those outliers traditionally just destroy the accuracy of low-precision integer formats.
Because the fixed point system just can't handle that massive dynamic range.
And this leads us to the central idea the sources reveal almost immediately. This INT versus FP choice, it isn't universal.
It's not a one-size-fits-all solution.
No, it depends entirely on this crossover point,
right,
which is determined by how we structure the data before quantization. It's an issue of scale and precision working together.
To really get that crossover, we first need to be clear about what we mean by granularity.
We're not just talking about bit width, 4-bit or 8-bit. Granularity defines the scope of the scaling factor that you apply to the data.
Right, so think of it like this. Coarse-grained quantization applies one single scaling factor to a huge chunk of data, maybe an entire tensor.
And if you have just one huge outlier in that chunk,
it ruins everything. That one outlier forces the whole scaling factor to be tiny, and you waste most of your precious bit budget.
Whereas the analysis here focuses on something different, fine-grained block-wise quantization.
So breaking the tensor into much smaller groups.
Much smaller.
Yeah.
And calculating a separate scale factor for each of those little groups. The formats we're looking at today are things like microscaling, or MX, which uses a block size of 32.
And Nvidia's format, NV, which often uses an even smaller block size of 16.
And by using these small blocks, you isolate the outliers. You make the data more uniform within each block.
And that isolation is, that's the whole key to letting these INT formats even have a chance.
It is. And to measure how effective these formats are, the sources mainly rely on the quantization signal-to-noise ratio, or QSNR.
A high QSNR just means the quantized number still holds the essence of the original signal.
So if QSNR is our measure of fidelity, the main predictor for whether INT or FP will give you a better QSNR is a variable called the crest factor. It's represented by kappa.
The crest factor. That sounds like a concept from, electrical engineering. How's it defined here?
It's the ratio of the maximum absolute value in a block to the root mean square of that same block.
So the biggest spike compared to the average signal power.
Basically, yeah. It measures how bad the outliers are relative to everything else in that one small block.
Okay, that makes a lot of sense. If you have a huge crest factor, a big kappa, it means you have one giant isolated spike. The dynamic range is huge.
And that's where floating point is great, because it's built to handle huge exponents.
But if you have a low kappa, the data is more well-behaved, it's more compact.
And that's the point. The sources established that these finer-grained blocks significantly reduce this crest factor. It shrinks the dynamic range needed, and suddenly it's a level playing field for the fixed-point INT formats.
So this framework lets us model the exact kappa threshold, the point where the advantage flips from FP to INT.
It does. We can get to specific numbers.
Okay, let's get into those thresholds, because they're the crucial prediction we need to test. We know FP wins in coarse, high kappa situations. But what about for these fine-grained formats?
For 8-bit precision, the sources found that the fine-grained MXINT8 format should outperform MXFT8 when the crest factor, kappa, is less than 7.55.
So 7.55, that's our 8-bit line in the sand.
It is.
And what happens when we go down to the really efficient 4-bit domain?
Well, the crossover point drops radically. It just shows how hard it is to handle any big outlier in such a narrow bit width.
So what's the number?
For MXINT4, kappa needs to be less than 2.04 to beat MXFP4. And for the NV format, NVNE4 needs a kappa below 2.39 to win. These are really tight tolerances.
So 7.55 for 8-bit and around 2.0 to 2.4 for 4-bit. We have the theoretical map. Now let's see how actual LLMs measure up against these numbers.
So the first empirical test was to analyze the intermediate tensors, the activations, the weights, from a model like Llama 3.18b.
Using real data, sequences from the Wikitext2 dataset.
Right. And first, if we look at the coarse-grained scenario, it kind of confirms why the industry has been so FP-centric.
What did they find?
With coarse per channel quantization, the 75% quantile crest factor. So the typical worst case was 11.97.
11.97. That is way above the 8-bit threshold of 7.55.
Way above, so that confirms it. For coarse quantization, FP's superiority is totally justified.
But the whole point of this investigation is the fine-grained methods. So when they switch to the fine-grained MX format with that block size of 32, what happens to that crest factor?
It just collapses.
Yeah.
The 75% quantile kappa drops from almost 12 all the way down to 2.96.
2.96. Now, that is significantly below the 8-bit threshold of 7.55.
It is.
So based purely on real LLM tensor stats, fine-grained MX-INT8 should theoretically always outperform MX-FP8. I mean, that's a major hardware revelation right there, and challenges the whole idea that FP is fundamental for LLMs.
It is a huge deal. But the story gets a bit more complicated at lower bits. While 2.96 is great for 8-bit, it's still above the MX-INT4 crossover of 2.04.
Ah. So the tensor analysis suggested that at 8-bit, fine-grained INT wins, but at that crucial 4-bit level, FP should still have the edge.
That's what the data suggested.
Which brings us to the direct cast inference tests. This was done across a whole set of 12 different LLMs using metrics like KL divergence to measure the total error. This is where the theory meets reality.
And for 8-bit, it held up powerfully. Comparing MX-INT8 against MX-FP8 with no special tricks, MX-INT8 outperformed MX-FP8 on all 12 models.
Confirming its dominance at fine granularity.
Complete dominance.
But the initial 4-bit results must have been a bit disappointing then, since the crest factor was still too high.
They were. Just like the theory predicted, the ultra-low bit integer formats, MX-INT6, MX-INT4, and VINT4, they all performed worse than their FP counterparts on all 12 models.
And that result has been the historical roadblock, right? That's what pushed hardware designers toward FP in the first place.
For sure. The immediate takeaway would be, if you want high efficiency at 4-bit, you have to stick with FP. But this deep dive didn't stop there. It introduced an algorithmic fix.
A mitigation technique.
A mitigation technique. The researchers applied something called random Hadamard rotation before the quantization step.
And what does that do?
It's a technique that's known to kind of smooth out the activation distributions. Think of it as shaking a jar of rocks until the sharp, spiky edges are less pronounced.
Which makes it much easier for a narrow 4-bit integer format to capture the signal.
It had a dramatic, measurable impact on the data. After applying this rotation, the crest factor for the NV format dropped from 2.39 down to 2.11.
And 2.11 is the magic number. It's now below the theoretical NVNT4 crossover point of 2.39.
So the algorithmic tweak successfully pushed the real-world data into the region where the integer format is supposed to win.
And the inference results confirmed it worked. So after rotation, MX-INT8 still wins on all 12 models.
But the major shift is that NVNT4 now wins on all 12 models as well. It surpasses NVFP4 in accuracy.
That just completely rewrites the story for 4-bit efficiency.
It really does. It shows the limitation wasn't, inherent to the integer format itself, is the data distribution. And if you fix the data with a simple algorithmic step, suddenly the much more hardware-efficient integer formats are not just viable, they're superior.
That's really compelling for inference. But high-efficiency formats also have to support stable training, right? Otherwise, they won't get adopted.
The hardware community needs to know they can train these huge models without losing accuracy. So the sources did a thorough investigation into low-bit training, specifically comparing MX-INT8 and MX-FP8 on Llama 3 style models.
And the finding was that MX-INT8 supports what they called nearly lossless low-bit training.
Nearly lossless, meaning they achieve performance almost identical to the high-precision BF16 baseline. This was across critical tasks, common sense reasoning benchmarks like HelloSwag and Wino Grande.
And not only was MX-INT8 competitive, it was a little bit better than its floating point rival.
It was. MX-INT8 consistently recorded a slightly lower loss by about 0.001 than MX-FP8 during the whole training process.
Now, to get the stability for INT during training, they had to introduce an innovation, didn't they? Something called symmetric clipping? Why was that needed?
It addresses this subtle but persistent numerical bias that's just inherent to standard signed integers, the 2's complement representation.
Ah, right. So for an 8-bit signed integer, the range is asymmetric. It goes from -128 up to 127.
That one extra negative slot,
Hmm.
it creates an imbalance. And when you're doing this fine-grained quantization, dealing with these tiny localized blocks,
Hmm.
that asymmetry can show up as a persistent negative gradient bias during training.
So symmetric clipping just forces the range to be symmetric, like -127 to
It
127.
does, a subtle fix, but it was crucial for ensuring the INT format stayed stable during optimization.
So we've got algorithmic superiority, we have training stability. The final and maybe most commercially important piece is the actual hardware cost, energy and chip area.
The sources analyzed the hardware cost of the matrix multiply unit, the MMU, which is the real engine of an accelerator.
Okay.
They compared the silicon area and the energy use at matched throughput.
So making sure both INT and FP units were processing data at the same speed.
A true apples-to-apples comparison.
And this provides the final, really powerful argument against the current FP trajectory. If we just look at single format efficiency.
The numbers are stark. MXINT8 reduced energy consumption by 37%. INT4 achieved a 38% reduction in energy compared to their FP counterparts.
Those are massive efficiency gains. For anyone running large data centers, savings like that are, they're everything.
It's direct savings on power, on cooling, on overhead.
And that's just energy. What about chip area? That dictates manufacturing costs, how much power you can fit onto a single piece of silicon.
Well, when they considered a chip designed for mixed precision, so supporting both 8-bit and 4-bit, they modeled a combined integer setup, MXINT8 plus NVINT4, versus a combined floating point 1.
And the result for area.
The combined INT configuration reduces the required chip area by about 34% compared to the mixed FP1.
A third less area. Just think about what that means. You can fit 1/3 more processing power onto the same die, or make the same chip for a third less cost.
From a business perspective, the case for leveraging fine-grained integers becomes almost undeniable.
It's really remarkable. So to synthesize all of this for you, the systematic comparison really just shifts the whole debate. While FP is fine for coarse granularity, these fine-grained INT formats seem to offer a superior overall balance.
Specifically, MXINT8 consistently outperforms MXFP8 in pretty much every metric: accuracy, training stability, and hardware efficiency.
And at that coveted 4-bit level, INT formats like NVINT4 can be made superior to FP.
But only when you strategically pair them with algorithmic techniques like Hadamard rotation to get that crest factor down.
So these findings really present a powerful challenge to the current FP-centric trajectory in AI hardware design. It suggests the focus has been maybe a little misplaced.
It shows that the future of efficient AI accelerators isn't about finding one universal format that rules them all. Success is going to require strategic algorithm hardware co-design.
A deep collaboration between the software and the silicon.
One that has to now prioritize the systematic adoption of these fine-grained integer formats if we want to maximize both performance and, our power savings.